Hello friends. Today in the subject Basic Electrical and Electronics Engineering, we will take up Unit 2.0, that is AC circuits. In that we will understand about alternating current fundamentals. So what is alternating current fundamentals? We will understand in the subject. Myself Chandrasekhar S. Patil, Sharad Institute of Technology, Polytechnic, Yadrao. The contents of this discussion are: first one, alternating current fundamentals; second one, advantages of alternating current over direct currents; third one, applications of alternating current and direct currents; fourth one, generation of alternating current and voltage; fifth one, elementary alternator operation of alternator; sixth one, graphical representation of EMF or current. Alternating current fundamentals. So we'll understand about what is DC and what is AC current. Advantages of alternating current over DC direct currents, and applications we'll understand. Generation of alternating current and voltage we'll understand. Elementary alternator operation of alternator. How does the alternator operate and how AC current is produced, we'll understand in this. And how AC is represented as EMF, graphical representation of EMF or current. Alternating current fundamentals. An electric current is classified into following two basic types: direct current and second one is alternating current. Always an electric current is classified as direct current and alternating current. The direct current is that which flows continuously in one direction and has constant magnitude with respect to time. The direct current is that in which it flows continuously. It doesn't change in magnitude or in direction and has a constant magnitude with respect to time. With respect to time, it is always having a constant magnitude. Alternating current. An alternating current is one which periodically passes through a definite cycle of changes in respect of magnitude as well as direction. Alternating current is that current which changes periodically in both in magnitude and also in direction. So that is called as alternating current. Each cycle consists of two cycles. During one of these half cycles, the current flows in one direction around the circuit and the other in opposite direction. Okay. So as shown in the graphical representation, in the positive half cycle, there are two half cycles in the alternating current. In the positive half cycle, what we do is the direction of current will be in one direction and the magnitude will keep on changing. And after that, in the second half cycle, the direction will be opposite and the magnitude again it keeps on changing from minimum to maximum. So this is shown in the graphical representation as shown in the figure B. While flowing in one particular direction, the magnitude of current changes regular manner with time. Always the magnitude of the current, whenever there is change in direction, the magnitude also changes in particular manner, in a regular manner with respect to time and in a particular direction. Advantages of alternating current over direct currents. Since it is possible to build up high voltage, high speed AC generators with very large capacities, their construction and operating costs per kilowatt are low. This is not possible in case of DC generators. So, the high voltages and it is possible to build up high voltages. We can build up very high voltages in case of alternating currents. High speed AC generators with very large capacities. We can generate high voltages similar to high speed AC generators with very large capacities. Their construction and operating costs per kilowatt are low. AC alternating current generation is easy and the cost and operating costs per kilowatt are low. This is not possible in case of DC generators, but in DC generator it is costly and it is not cumbersome to generate DC currents of the high voltage level. The AC voltage can be raised or lowered very easily with the help of a static device known as transformer. Raising and lowering of DC voltage is not so easy and economical. The AC voltage can be raised to high voltages with the help of a transformer, with the help of a static device called as transformer. But in case of DC, the raising and lowering of voltages is not easy and it is not economical. Due to adoption of high voltages, AC transmission is always efficient and economical. This is because higher the voltage, lesser is the current flowing through the transmission line conductor from the given power, for the given power. Consequently, the weight of the conductor material and the power loss in the line itself are reduced. So, by the adoption of high voltages, AC transmission is always efficient and economical. It is always efficient and economical because at high voltages, the lesser is the current and higher is the voltage and the flowing through the transmission line for the given power. Because of that low current value, we have the size of the conductor reducing, and because of that we have losses, I square R losses are minimized. AC motors are simple in construction. Always the AC motors are simple in construction, cheaper and more efficient than DC motors, and require less maintenance. So the AC motors are simple in construction, more efficient than DC motors, and also require maintenance cost is very less and also requires less maintenance. AC can be easily converted to DC whenever required for some specific applications. So we can understand that always AC can be converted into DC easily with the help of rectifiers, that is half wave and full wave rectifiers, easily for some specific applications. Applications of alternating currents and direct currents. So we have to understand what are the applications. Now we have understood what is an alternating current and what is a direct current. Okay. Now we will understand what are the applications for direct currents. Traction, railways, electric trains, and or these metro trains, or all these trains are called you have the applications of direct currents. Electrolytic and other chemical processes. If you want to generate any chemical or if any electrolytic process is going on, then we have to go for direct currents. Then we have third one, arc lamps, used for searchlights and cinema projectors. Whatever the lights we see in a cinema projector or arc lights, searchlights, that are based on direct currents. Telephone and telegraph systems. Whatever telephones phones, landlines we are using, that is requires direct currents, and telegraph system also requires direct currents. Charging storage batteries. Storage batteries, if you want to charge, then we have to give direct current supply. Modern protection system, etc. Any protection system is there, any PCB based or microcontroller based, microprocessor based protection system is there, then we have to go for direct currents. Applications of alternating currents. AC motors, alternating current motors, induction motors, AC motors, all these are applications of alternating currents. Then we have transformers. Transformers are also used, which is a static device used to generate high voltages and also to step down the voltage. It is used for step up and step down of voltages depending upon the number of turns in the primary and secondary. This we have understood in the previous lectures about transformers. Lamps. We have to, whatever induction of incandescent bulbs or lamps we are using, that is working on alternating currents. Then we have fans. Fans which we are using in our rooms, that is based on induction motor, and we have the application of alternating currents. Majority of domestic applications such as TVs, refrigerators, washing machines, boilers, geysers, mixers, air conditioners, and innumerable other applications. All the domestic applications like televisions, refrigerators, boilers, washing machines, geysers, mixers, mixer grinders, air conditioners, ACs, air conditioners, and innumerable other applications require the alternating current supply. Generation of alternating current and voltage. How to generate an alternating current and voltage? So, an electric current, whether DC or AC, is now commonly produced by means of an electric machine known as generator or alternator, which converts mechanical energy into electrical energy. Generally, whatever electricity we are producing, most of the electricity produced is through a machine called as generator, which converts mechanical energy into electrical energy. Principle of generator. How does generator work, or how does generator produce alternating current and voltage? The operation of all electric generators, whether DC or AC, is based on the fact that when a conductor is moved in the magnetic field or a magnetic field moved with respect to the conductor, according to Faraday's law of electromagnetic induction, or an electromotive force is set up in the conductor. Thus, as long as there is a relative motion between a conductor and magnetic field, a voltage will always be generated in the conductor. So, according to Faraday's law, we have understood about statically induced EMF and dynamically induced EMF. Okay. So, in the statically induced EMF, whenever the conductor is stationary and the flux is changing, then we have a statically induced EMF. Similarly, whenever there is conductor movement in the magnetic flux, we have a dynamically induced EMF or current. So, these are the two laws of Faraday's law of electromagnetic induction. In either case, there is a relative motion between the magnetic field and the conductor, and at that point of time, electricity or EMF is generated in the conductor. AC generators are normally known as alternators. Always the AC generators are normally known as alternators. Elementary alternator construction. It consists of single turn. What is an elementary alternator? How does the construction of the alternator looks like is shown in the diagram. It consists of a single turn rectangular coil AB made up of some conducting material like copper or aluminium. The coil is so placed that it can be rotated about its own axis at a constant speed in a uniform magnetic field provided by the north and south poles of the magnet. The coil is known as armature of the alternator. Okay. The ends of the armature coil are connected to the rings R1 and R2 called slip rings, which rotate with the armature. Two carbon brushes B1 and B2 pressed against the slip rings collect the current induced in the coils and carry it to the external circuit. So, in the construction of the elementary alternator, there is a coil AB made up of conducting material called copper or aluminium. It may be copper or aluminium material. There is a conducting material which is in the form of AB. The coil is so placed that it can be rotated about its own axis. It is so placed that it can rotate about its own axis. It can rotate on itself in a uniform magnetic field provided by the north and south poles of the magnet. There are two magnetic poles, north and south pole, and the coil AB rotates around its own axis around the magnetic field in the presence of the magnetic field between the north and south poles. The coil is known as armature of the alternator. It is also known as armature of the alternator. The ends of the armature coil are connected to the rings R1 and R2 called slip rings, which rotate with the armature. At the ends of the coil AB, which is shown here in the diagram, there are two slip rings R1 and R2, and these collect the current which is generated during the relative motion between the magnetic field and the coil. Two carbon brushes B1 and B2 pressed against the slip ring collect the current induced in the coil and carry it to the external resistor R. Whatever the current is produced, that is taken up by the brushes B1 and B2, which is connected to the slip rings of the alternator, and they carry the current to the external circuit R. Operation of alternator. How does alternator operate? Now we have understood what is the construction of the alternator and how actually the EMF is produced, or how actually the current, induced current is produced. That we have to understand in the operation of alternator. Assume that the armature is rotating in anti-clockwise direction. So if we are rotating in the opposite direction to the direction of the movement of a clock, that is called as anti-clockwise direction. Armature is assumed to be moving in the anti-clockwise direction. As the conductors A and B of the coil cut the magnetic field, according to Faraday's law of electromagnetic induction, an EMF is produced in them which causes a current to flow through the external circuit. So whenever there is a relative motion between the magnetic field and the coil, a current is induced in the circuit, in the coil, and in the external circuit it senses a current. The magnitude of this EMF is dependent on the position of the armature coil in relation to the magnetic field. How is the position of the armature with respect to the magnetic field? That is also important whenever then EMF or current is generated. Let us consider the few selected positions of the coil as shown in the figure. So we are selecting some positions as shown in the diagram. First position, second position, third position and fourth position. First position at 0 degree with respect to the magnetic field, and second position is 180 degree with respect to the magnetic field. 90 degree with respect to the magnetic field. Third position is the 180 degree with respect to the magnetic field, and fourth position is 270 degree with respect to the magnetic field. So first position, this is the initial position of the coil, the plane of the coil being perpendicular to the magnetic field. Okay, the first position, it is perpendicular to the magnetic field. The conductors A, B of the coil move parallel to the magnetic field. Since there is no flux cutting, an EMF is generated in the conductor, and therefore no current flows through the circuit. Since initially the position 1, we are moving in the anti-clockwise direction. So the direction of the current is perpendicular, the direction of the coil is perpendicular to the magnetic field of the conductor, and because of that it is moving in parallel to the magnetic field, so we don't have the induced EMF. Since there is no flux cutting, no EMF is generated in the conductor, and therefore no current flows through the external circuit. Position number 2. As the coil rotates from position 1, phi is equal to 0 to position 2, phi is equal to 90 degrees, more lines of force are cut by the conductor. So whenever it moves from 0 degree to 90 degrees, more and more lines of flux are cut by the conductors. In position 2, both the conductors of the coil move at right angles to the magnetic field and cut through a maximum number of lines of force, so that EMF induced in them is also maximum. So more and more magnetic flux is cut. There is a relative motion between the magnetic flux and the conductor. Because of that, more and more EMF is generated at the position 2. In other words, 0 degree to 90 degree, the EMF builds up from 0 to a maximum value. The EMFs in both the conductors being in series with the resultant coil EMF is the sum of two conductors. It is therefore twice that of one of the conductors, since the voltages are equal. The current through the circuit varies just as the EMF varies, being from 0 to rising to a maximum 90 degree. So gradually the current varies from 0 to 90 degrees. In position 2 of the coil, according to Fleming's right hand rule, the direction of the induced EMF in the conductor A is towards the observer. Whatever the EMF is generated or the current is generated, that is towards the observer out of the plane paper, and in conductor B it is away from the observer, that is in the plane of the paper as indicated. So from A to B the current flows, means the conductor is moving, the coil is moving from 0 degree to 90 degrees. Because of that, the current flows out of the plane paper and from A to B. Therefore, the current flows to the external circuit from the terminal C to terminal D. As the coil continues to rotate further from position 2, phi is equal to 90 degree to position 3, phi is equal to 180 degrees, the lines of force are cut by the conductors gradually reduce. This decreases the generated EMF in them. So, as the coil rotates from 190 degrees to 180 degree, the lines of flux are gradually reduced. The force cut by the lines of force are cut by the conductors gradually reduced. This decreases the generated EMF in them. In position 3, the conductors again move parallel to the field and hence no EMF is induced in them. At position 3, what happens? It again moves in parallel to the conductor and EMF is not induced in them. Therefore, the current through the external resistor is also 0. At that point of time, the current through the external resistor is also 0. It should be noted that during the rotation of the coil from 0 degree to 180 degree, that is during the first half revolution, the conductors of the coil move in the same direction through the magnetic field. So, whatever the movement is there from 0 degree to 90 degree and 90 degree to 180 degree, at the position 1 and at the position 3, there is no induced EMF because the conductor is moving in parallel to the magnetic field. Therefore, throughout this period, the polarity of the EMF generated remains same and current also flows from the external resistor from C to D only. Position 4. As the coil rotates beyond position 3, the direction of the cutting action of the conductors through the magnetic field reverses. As the coil rotates between position 3 to 4, the direction of the flow of current also reduces. Now the conductor A cuts up through the field and the conductor B cuts down through the field. Conductor A cuts up and conductor B cuts down. In consequences, both the polarity of the generated EMF and the current flow reverse. The polarity of the EMF reverses and also the direction of current also reverses in the case of position 4. To make it more clear, consider the coil in position 4, phi is equal to 270 degree. By applying Fleming's right hand rule, it is seen that the direction of induced current in the conductor A is away from the observer and in the conductor B it is towards the observer. As such, current flows through the external resistor from D to C. Thus, during the entire second half revolution, that is when the coil rotates from position 3 to 4 and back to position 1, the current flows in the opposite direction to that of the first half revolution. Also, similar to position 2, EMF in the coil is maximum in position 4. Similarly, at position 4, phi is equal to 270 degrees, the maximum EMF is generated in the reverse direction compared to the position 1. In general, the variation in the magnitude of EMF of the alternator when the armature coil rotates from 180 degree to 360 degree are exactly similar to those in the first half revolution. Similar to the first half revolution, the magnitude will be same, only the direction will reverse. The direction will be in the reverse direction and the magnitude will be in the opposite direction to the first half revolution. Graphical representation of EMF or current. How do we represent the EMF is shown in the graphical representation shown in the diagram. The graph of EMF or current for the complete revolution of the coil under consideration is shown in the diagram. From the graph, it will be readily seen that the voltage and current supplied by such an alternator are alternating and follows a sine curve. In practice, an alternator has a number of poles and a number of coils suitably connected to obtain the necessary EMF. So, the graphical representation of a simple alternator is shown in the diagram. It is EMF or current with respect to angle, and the graph of EMF or current for the complete revolution of the coil under consideration is as shown. Okay. So, the voltages and the current gradually increase to a maximum in one direction and again it gradually reduces to 0, and again in the reverse direction the magnitude increases to maximum and again it reduces to 0. In practice, an alternator has a number of poles. Actually, in what happens in the real practical applications, there are a number of poles and number of coils, and suitably to obtain the necessary EMF. To obtain the suitable EMF voltages, we are generating number of poles and number of coils, and because of that, a suitable voltage level is generated. So with this we have understood how the alternating current is generated, what are the advantages of alternating currents over direct currents, and what is the applications of alternating currents and direct currents, and how actually alternating current is generated in a generator or an alternator, and what is the sinusoidal waveform representation of the alternated EMF or current. Thank you.